Usually when we talk about a medical diagnosis, there's this expectation of just absolute precision.
Right, like it's engineering or something?
Yeah, exactly. Like you break your arm, the x-ray shows that jagged white line, and the doctor just points and says, there it is.
It feels very binary, like it's either broken or it's not. It's clean.
Right. It's undeniable.
Mm.
But what happens when you aren't looking at bone? What happens when you're looking at a standard CT scan of soft tissue?
It's just a sea of blurry gray pixels.
Exactly, just gray pixels. But what if a computer could look at those blurry pixels and instantly tell a surgeon not just what kind of cancer you have, but exactly how it's going to behave in the future?
And crucially, do all of that without ever making a single physical cut into your body.
Right. Welcome to today's Deep Dive. We're so thrilled to have you with us as we unpack this truly groundbreaking, multi-cohort medical study.
Yeah, we're looking at a fascinating piece of technology today called MTV-Net.
So, to set our mission for you today, we are exploring this incredibly dense, data-rich clinical study that details a new artificial intelligence framework.
Right, an AI that essentially reads the vascular footprint of primary liver cancer from standard hospital scans.
And it was developed across multiple medical centers, tested on over 1,000 patients. So our ultimate goal today is to really unpack the exact mechanisms of this tech.
We want to take you all the way from the raw biology to the complex algorithms and down to the molecular genetics driving it all.
Because it's not just about spotting a tumor, right? It's about predicting its personality.
Exactly. And to understand what this AI, this MTV-Net, is actually doing, we first have to introduce the villains of our story.
The targets.
Right. We're talking about primary liver cancers, or PLC, and specifically the study looks at two major biologically opposed types.
Okay, lay them out for us.
The first is hepatocellular-carcinoma, which we'll call HCC, and the second is intrahepatic-cholangiocarcinoma, or ICC.
Okay, so HCC and ICC. And trying to picture how these two distinct cancers operate, I keep going back to the study's analogy of a city's infrastructure.
It's the best way to visualize it. We're looking at the tumor vascular microenvironment, or TVME.
Right, the blood vessel network feeding the tumor. It's like the city's plumbing and road system.
Exactly. So HCC, that first type, operates like a completely chaotic, leaky plumbing system.
Yes, it grows so fast, right?
Yeah, it grows rapidly and starves itself of oxygen. This state is called hypoxia. And in a total panic to survive, the tumor releases a protein called VEGF. And
VEGF basically yells at the body to build new blood vessels immediately.
Right, but because it's panicking, the construction is terrible, it builds this hyperpermeable sinusoidal vasculature.
So it's basically a network of leaky pipes.
Exactly. And that leakiness is the danger. It allows the tumor cells to just slip right into your bloodstream, leading to early microvascular invasion.
Wow. Okay, so HCC is the panicky, leaky plumbing. How does ICC compare to that?
If HCC is leaky plumbing, ICC is a reinforced concrete bunker.
A bunker.
Yeah, it behaves entirely differently. It's driven by completely different signaling, specifically FGFR and PDGF pathways.
And what do those do?
They create highly dense fibrotic capillary networks. It literally builds a thick stromal barrier, like a wall of tough tissue around itself.
Almost like it's armoring itself against the outside world.
Exactly. And that wall makes it incredibly resistant to chemotherapy and promotes late-stage lymphatic metastasis.
That is deeply unsettling. So you have one enemy that slips out through leaky pipes and another that just barricades itself behind concrete.
Right.
But here is the part that genuinely terrified me. When doctors use the current imaging standard, it's called LIR8S, to try and tell these two cities apart without cutting you open, the accuracy rate is only about 60 to 75%.
Which is a massive, life-threatening blind spot. That ambiguity is devastating.
So the treatments are totally different, right?
Completely different. Imagine a surgeon goes into the OR thinking they're fighting the leaky plumbing of HCC, but they actually hit the concrete bunker of ICC.
The chemotherapy, the surgical approach, it's all wrong.
Right. And you might ask, well, why not just do a biopsy?
Stick a needle in and test it.
But the study highlights why that fails. Biopsies are invasive and they suffer from massive sampling errors. You might poke the 1 millimeter of the tumor that happens to look different from the rest.
Right, you're judging the whole city based on one street corner. So to summarize this first part, liver cancers have these vastly different plumbing systems, but human eyes and current standards fail to reliably tell them apart up to 40% of the time.
It's a desperate situation.
So here's a question for you, the listener. If you were a doctor staring at a blurry scan, how would you peer through those concrete bunker walls without taking a scalpel to it.
That's the exact dilemma.
All right, we're at the 5-minute mark, so let's do a rapid-fire recap of what we've covered so far.
Let's do it.
Bullet 1. Primary liver cancers come in two main biologically opposed types, HCC and ICC.
Bullet 2. Their behavior is dictated by their tumor vascular microenvironment. It's leaky pipes versus concrete bunkers.
And bullet 3. Current non-invasive imaging fails to tell them apart up to 40% of the time, meaning we desperately need a new approach.
Which brings us perfectly to the technology itself, unpacking MTV-Net.
Yes. So MTV-Net stands for Multitask Vessel Computational Network, and it tackles this exact problem in a really fascinating way.
It does. The AI operates in 4 main steps. Step 1 is segmentation, using an algorithm called NNU-Net.
And this isn't just drawing a 2D square around a dark spot on an image. It's a 3D hierarchical tool, right?
Right. First, it automatically segments your entire liver. Then it precisely draws a 3D boundary, a region of interest around just the tumor.
And the craziest part to me is how it accounts for human movement, like isolating it across different respiratory motions.
Yeah, it basically subtracts your breathing from the math. It's incredibly precise.
So step 1 gets the tumor isolated, then what?
Step 2 is vessel phenotyping. This is where it maps the plumbing. It uses something called a Hessian-Frange filter.
Okay, the math here gets wild. But the best visual analogy I found was, imagine putting on thermal goggles. But instead of heat, these goggles only glow when they see tubular structures.
Blood vessels.
Right, blood vessels. If the tissue is flat or round, the goggles completely ignore it.
That's a great way to put it. Mathematically, the filter is computing second-order intensity derivatives, specifically Hessian matrix eigenvalues from the CT scans.
Okay, translate that for us non-math folks.
It basically calculates the exact rate at which a shadow turns into a continuous line, which amplifies continuous tube-like networks and dims out all the static noise.
Ah, okay, so it isolates the 3D plumbing, which leads to step 3, extracting the 78 quantitative vascular features, or
Right.
QV features.
Right. And how do they get exactly 78? It's exhaustive math. First, they extract 13 histogram features.
Like the minimum maximum range, kurtosis.
Skewness, energy, entropy, basically measuring the chaos of the structure.
Right. Then it multiplies those 13 features by 3 spatial tumor zones.
Which are the full tumor, the inner central zone, meaning a radius of 5 millimeters or less, and the outer peripheral annular zone.
Okay, so 13 times 3, that's 39.
And then you multiply that by 2 CT scan timing phases.
Oh, this part blew my mind. So phase 1 is the arterial phase.
Exactly 30 seconds after a contrast dye is injected into the patient.
And phase 2 is the portal venous phase at 60 seconds post-injection. So 13 times 3 times 2 equals 78 highly specific features.
Right.
But wait, why does the time matter so much?
Because a tumor is a dynamic ecosystem. At 30 seconds, blood is rushing through the arteries. At 60 seconds, it's pooling in the drainage system. The AI watches the blood flow in real time.
That's brilliant. So the final step, step 4, is the algorithm itself. The RMTL, or regularized multitask learning pipeline.
Historically, you'd have one AI to guess the tumor type and a separate one to predict survival. RMTL does both simultaneously.
It uses a cross-task regularization penalty?
Yes, the L21 norm. It essentially forces the network to find shared biological patterns between the diagnosis and the future behavior.
Amazing. So to summarize this subtopic, the AI segments the tumor, puts on its Frange goggles to map the 3D plumbing, extracts 78 math features across space and time, and trains itself on 2 clinical tasks at once.
Exactly. So here's a question for you listening at home. Why do you think measuring the outer ring of a tumor's blood supply at exactly 60 seconds is just as critical as measuring the core?
It really makes you think about how tumors interact with the healthy tissue around them. But all right, moving on to segment 3. We have this amazing tech. How did it do in the actual clinical trial?
The dataset was massive, 1,020 patients across 6 distinct cohorts.
5 in-house Chinese medical centers and 1 public database, right?
Exactly, the TCIA database. And from this, the AI generated 2 golden tickets for every patient.
Right. Golden ticket number 1, TVSPHE, the tumor-associated vessel score for phenotyping.
This score predicts if the tumor is HCC-like or ICC-like, and the accuracy was incredible, an AUC of 0.949 in external validation.
That's about an 82% overall accuracy, which is vastly superior to the human eye.
Vastly. And the second ticket is TAV-SRE. the tumor-associated vessel score for recurrence estimation.
Basically stratifying the patient into high risk or low risk for the cancer returning after surgery.
Right. And when the researchers combined these two scores, they created 4 distinct imaging subtypes, graded evidence.
Let's look at the extremes. Subtype 1 is HCC-like and low risk.
This is the best prognosis. Patients here had a 3-year overall survival rate of 83.1%.
But then you have subtype 4, ICC-like and high risk.
The worst prognosis, a 3-year overall survival of just 9.1%.
Just 9%. And what's wild is how they combined MTV-Net with traditional clinical staging, like the TNM or BCLC systems doctors already use.
Yeah, it pushed the predictive concordance index, the C-index, from the 0.60s all the way up to a highly accurate 0.731 to 0.823 range.
So it's not replacing doctors, it's supercharging them. To summarize, the AI spits out 2 scores classifying physical shape and aggressiveness, creating a 4-tier matrix that just blows traditional staging out of the water.
Absolutely.
So listener, think about this. If a patient is diagnosed with subtype 4 instead of subtype 1, how might that fundamentally alter a surgeon's aggressiveness in the operating room?
It changes everything.
Okay, we've hit the 10-minute mark. Time for recap number 2.
I'm ready.
Bullet 1. The NNU-Net and Hessian-Frangi algorithms work together to isolate the tumor and extract exactly 78 vascular features.
Bullet 2. This multitask learning generates 2 biomarkers, TAV-SPHE for subtyping and TAV-SRE for recurrence risk.
And bullet 3. Blending these AI scores with traditional clinical models creates a hyper-accurate 4-tier risk stratification system.
Which brings us to the ultimate test. Segment 4.
Oh, the boss fight.
The boss fight of liver cancer diagnosis. We're talking about CHC combined hepatocellular-cholangiocarcinoma.
Which is exactly what it sounds like. It's a tumor that has features of both HCC and ICC.
Yeah, it's a hybrid. It completely confuses human pathologists and basically renders current imaging useless.
To ground this in reality, let's look at the actual patient case studies from the paper. Case number 1, a 58-year-old male with a 3.3 by 3.6 centimeter nodular lesion in segment 6 of his liver.
To a human, it's just a blurry mass, but MTV-Net analyzed him and printed out HCC-like and low risk.
Right. KV-SPHE of 0.081, KV-SRE of 0.650, and the result, he is alive and recurrence-free at his 56-month follow-up.
Now contrast that with case number 2, a 71-year-old male. Almost identical tumor size, 3.5 by 3.8 centimeters in segment 4.
MTV-Net evaluated the exact same type of blurry scan, but outputted ICC-like and high risk.
A negative TAV-SPHE of NAGNA 0.448 and a high TAV-SRE of 0.746, and the tragic clinical result.
He relapsed at just 9 months and passed away at 17 months.
The AI saw the danger hiding in the noise, and the massive statistical validation proved it wasn't a fluke. CHEC patients classified as ICC-like by the AI had a massive 69.7% recurrence rate.
Meaning the AI isn't just looking at the most common cells, it's actively recognizing the deadly concrete bunker vascular phenotype hiding inside a mixed tumor.
Exactly. It spots the worst-case scenario.
Summarizing this part, MTV-Net thrives on the most ambiguous cases, accurately splitting a hybrid cancer into reliable buckets of survival.
It's powerful.
So hearing the contrasting fates of the 58-year-old and the 71-year-old, does knowing an AI can predict a patient's timeline with such clinical coldness make you feel more empowered or slightly unnerved?
It's definitely a double-edged sword emotionally.
It is, which leads to segment 5, opening the black box.
This is a huge issue. Doctors hate black box AI.
Right, if a computer can't explain why it made a choice, surgeons will not trust it with a human life.
Nor should they. So the researchers had to prove the AI's logic. First, they used something called SHAP values.
Shapley additive explanations. It basically forces the AI to rank exactly which of the 78 features it cared about most.
And the detail here is fascinating. The portal venous phase features, the ones at 60 seconds, they drove the subtyping of HCC versus ICC.
But the arterial phase features at 30 seconds were pivotal for calculating recurrence risk.
Right. The AI uses different moments in time to answer completely different biological questions.
That's so smart. But they went even further. The pinnacle of the study.
Radiogenomics.
Yes. They mapped the AI's imaging phenotypes against actual bulk RNA sequencing data.
Using algorithms like GSEA and WGCNA.
Okay, so they linked the pixels to the actual DNA, but can we unpack that? What are the molecular mechanisms here?
It all comes down to the extracellular matrix, or ECM. The ECM isn't just a static scaffold holding cells together. It's a dynamic environment.
It's the soil the cells grow in.
Exactly. And the biological root of both AI scores is ECM remodeling.
Okay, so what happens when that sodium mutates?
It causes ineffective angiogenesis. The tumor is desperately trying to build new blood vessels to feed itself, right? But because the ECM is chemically chaotic, the resulting blood vessels are completely immature, leaky, and disorganized.
Wait, so that chaos is exactly what the Frangi filter is picking up on the CT scan?
Yes. That chaotic structure is what allows tumor cells to easily escape into the bloodstream, driving that high recurrence rate.
Wow. So to summarize this, by linking AI pixels directly to genetic sequencing, the researchers prove the AI is actually seeing the physical manifestations of DNA mutations.
A broken extracellular matrix creating chaotic blood vessels.
It's incredible. So question for you. We're literally seeing genetics translated into pixels on a screen. What other invisible biological processes do you think AI could uncover from a basic, everyday medical scan?
The possibilities are endless.
All right, 15-minute mark, our final rapid-fire recap.
Let's hear it.
Bullet 1. MTV-Net accurately diagnosed and predicted survival for CHC, which is the most confusing hybrid liver cancer out there.
Bullet 2. SHAP values open the black box, proving the AI relies on distinct time phases of blood flow for its predictions.
And bullet 3. Radiogenomics linked these AI-detected vessel shapes directly to ineffective angiogenesis and chaotic ECM remodeling at the genetic level.
The perfect summary.
And that brings us to the end. I really want to thank you, the listener, for going on this deep dive into the microscopic world of tumor vascular microenvironments and the algorithms built to decode them.
It's a lot of complex science, but it's so important.
It really is. But before we go, I want to leave you with a final provocative thought.
Go for it.
If AI can look at the physical architecture of a blood vessel on a basic CT scan and accurately infer the exact genetic mutations and protein pathways driving it, are we rapidly entering an era where the concept of an invasive tissue biopsy becomes entirely obsolete?
It's a huge question.
Right. I mean, if pixels equal genes, the scalpel might soon be permanently replaced by the algorithm.
I invite you to really mull that over. Share your thoughts on how AI will change your own future medical visits, and just keep questioning the data around you.
Absolutely. Thanks for exploring with us. We'll catch you on the next deep dive.